Hello, this is Python's Asyncio in C++ for terminal graphics, indeed. I'm Fernando, and thank you all for being here. So this talk is about a C++ coroutines, C++ 20 coroutines use case using Asyncio in C++. And Asyncio is Python's library to write concurrent code using the async and await syntax. So this project started from a need, tooling need, a bit for fun. I like doing programming puzzles, and I like doing visualization sometimes for them. Sometimes they help debugging, but also just sometimes I think it's just a bit more extra fun. And yet, so normally I do these things just printing some output into the console, and I started surveying graphics libraries to get some more features for these animations that I was doing. And yeah, I eventually found about a library written in Python using Asyncio that was for terminal graphics. And yes, so I had heard a little bit about C++ 20 coroutines, but never used them. And I saw that the syntax that this library had in Asyncio was using await, and I became curious to see if it would be possible to actually get to co-await of Python code. So that's a bit how it all started. And I will link that with a bit of a disclaimer. So yes, when I started looking into this December last year, I had no experience with C++ 20 coroutines or the async await syntax. So there are for sure suboptimal parts in the solution that I will be showing here. And in fact, there is one function where I'm doing an wait to a stud feature with an explicit timeout that I think it would be more elegant to solve without needing to have that parameter. So even if for the animation that I have been doing, so let's say in practice for this use case, is I don't expect that it really change. But yes, I think it will be more elegant solution. So yes, my goal with this talk is just to share a bit what I have managed to put together in order to achieve that. That is using asyncio from C++. So being able to eventually, we will build to that during the talk by first doing asynchronous interoperability between the two languages without using C++ coroutines, like step by step. But yes, just to share a bit the process and eventually how to get to that. So outline of the talk. So I'll start from let's say from scratch with Python and C++ interoperability using a specific tool called PyBind11. And here the focus will be to use Python from C++. So at the moment there won't be any asynchronous code, just importing modules and instantiating Python objects from C++ via PyBind11 and calling functions accessing data members. After that, I'll have one slider introducing the terminal graphics library built on top of Asyncio that I mentioned. It's called batgrl, or that's at least how I pronounce it, even if it doesn't have the I in there. And then we will get to the two main sections of the talk. So for each of these sections, I'll be using a terminal animation built on C++ using this library as a running example. So in section 3, this will be an animation of 3D cubes in the terminal that is interactive using a class offering this feature from the batgrl library. And then in section 4, I will be using a rock, paper, scissors animation. So it's like if you would be playing against the computer, which is selecting at random one of these in turns. So in section 3, there will be only asynchronous side on the Python land, and we will be using that from C++ and also writing code in C++ conforming to Python's interface for asynchronous code, like a coroutine. But there won't be use of C++ 20 coroutines then. That will be in the second part of section 4. So at the beginning in section 4, for rock, paper, scissors, it will be using add-on callback, so a callback interface from Python's asyncio task. And then I will try to illustrate how that can be improved, at least from the sense of conciseness in the syntax, using the await syntax, or in particular in C++ using the co-await keyword. And at the end, in the last session, I will have just one slide with some summary and conclusions. So let's start with general Python and C++ interoperability focus around Python 11. So first, I have 3 citations to other talks in the C++ community on this topic. So already back in 2016, Diego gave a talk on Introduction to C++ Python Extensions and Embedding Python in C++ apps, where he also discussed Python 11 as well as other tools for interoperability, like we can see there on the slide, Boost Python. Next year, also on CPPCon, Jan gave a lightning talk on Python 11, Python on steroids. And more recently, last year in CPPCon 2023, Saxon talked about writing Python bindings for C++ libraries, easy to use performance. So in these two last citations, in the talk, in the lightning talk by Jan and in this one by Saxon, the focus was on leveraging C++ from Python, which is, I believe, at least the usual direction of interoperability that is of interest when working with these two languages. But in this talk, as well as something that Diego mentioned in the other talk, the focus is on using Python from C++. And this is using Python 11 naming is what is called embedding, from embedding the interpreter, the Python interpreter in C++ apps. So let's start just by looking in detail how that is done in code. So yes, we start with an include from Python 11, the embed.h header. And once we include that, we get access to some things, among them, importantly, the scope interpreter. And yes, so also here I'm putting a shorthand that we will be seeing usually in the slides. So Python 11 namespace, just shortened by Py. And yes, so when we want to use anything from Python, like importing a module or calling methods from Python objects from C++ using Python 11, we will have to have instantiated this scope interpreter and keep it alive. Then once we have the scope interpreter, we can start doing imports. So if you are familiar with a bit of Python, usually Python scripts, .py files, start with imports, import and then the name of the module. And this is how it looks when we are using Python 11. And there I have just put like 3 libraries that I believe are popular, but just as examples. And yeah, so we see here that we get this import function from a Py module. Then we are passing the name of the module as a string. And what we get back is a Pybind 11 object, a Py object. So in most cases that we have Python objects in the C++ application, when we are using Pybind 11, it will be a Py object, the type that we are dealing with. And yes, so this Py object is has a attr method that is going to allow us to call functions or access data members if we have objects, or also the same method, it will allow us to call methods from objects. So you will look that in a particular example here. So here we have just a quite minimal yet complete C++ application using Python 11. So where I have put together the things that I was mentioning in the 2 previous slides. So we have the include of embed.h, then the shorthand for the namespace, and then yes, in the main function. So importantly, instantiating the scope interpreter, And once we have the interpreter in scope, so we can do imports. So in this case, I'm importing yet another widely used Python library, at least I believe. So it's for doing HTTP request, or yes, interacting with HTTP. And yes, so here I'm just getting from that module, I'm using the function get, passing URL, so just getting the URL of the conference. And then on the last line, on line 9, so there I'm using another method of pybind11 to print objects on the console, and the attr method, at this time to access a data member from an object. So here, if we contrast lines 8 with 9, in line 8, we are using attr to call a function from a module, and then in line 9, we are using the same method, attr, but this time in order to access a data member from a pybind object. Okay, so that was a bit introduction to interoperability between Python and C++, focusing on using Python from C++ using pybind11. And now just one slider introduction to the batgrl terminal graphics library. So yes, batgrl is an open source library available in GitHub, written in Python, about 30,000 lines of code, although I think when I did that count is also counting the examples. So let's say the main library code is probably some lines less, but still it's a medium, perhaps large, slightly large Python code base. And yes, so the motivation here is so instead of just rewriting the library in C++, for instance, so that it can be interesting just to use this Python code from another programming language. In my case, I feel comfortable using C++. I like using it for these puzzles. So yes, I thought that was the motivation. And yeah, so also the library is built on top of Asyncio, so the Python library to write concurrent code with async await syntax. And then yes, so we will be seeing how we can use co-await in C++ to use the library. But first of all, let's start with simpler interoperability challenges. So throughout the next slides, I will be building towards this cubes 3D app visualization that I mentioned. So yes, app is a class in batgrl, and is a class that we will be inheriting from to create our own visualizations in C++. So I will call normally also the visualizations like batgrl apps. So yes, so throughout the next slides, we are going to be seeing how, in general, a class that has been written in Python can be derived from C++ using pybind11. So in this case, it would be the app class that we are deriving. And we will do this to implement an abstract method of the class. So we will see this in more detail, but the app class, it has a method called run that is going to be like the entry point for the terminal visualizations. And then it has an abstract method called onStart, where we are going to put the logic that we want our terminal visualization to have the logic, and also how the visuals also they look. Yeah, so if we are using Python terminology, so it's app. The app class would be an ABC, an abstract base class. If we would be using C++ terminology, it would be an abstract class, and then the onStart method is like if it were a pure virtual method in C++. In Python, that's decorated with the abstract method. And yes, so once we have seen that part of the interoperability, we will see how we can make that method that we will be implementing from C++ as a pybind11 binding, how we can make it compatible with Python asyncio. So here it's the code to do new class in C++ using Python 11 that derives from a class that is written in a .py file. So in the two first lines, there is nothing of inheritance yet. We are just importing what will be the parent class. So just getting the app class from the batgrl app. And here I'm calling it just app class in a when it has the pybind 11 py object type. Now, on these next two lines, so what we are getting is we are getting the Python's type in the C API layer. So this is PyType type. We are getting the memory address to that. That's what is happening on line 5. And then on the right-hand side of line 4, we are using a function from Python 11. We will see in the next slide with links to documentation these two parts a bit more in detail, and also just for later if someone is interested to check more. But yes, we are just getting there the memory address and making it so that we can use it from Python 11. Excuse me 1 second. I'll drink a bit more. And yes, so once we have that object, I'm calling it meta class since it will be, I will use it in order to create the new class. And that's what is happening on lines 7 and 8. So this meta class, I'm giving it 3 arguments. In the first one is a string with the name of the new class. Now, in the second class is where we are specifying what are going to be the parent classes of this class, which in this use case, I only want to have one of them, which is the app class. And then in the third and last argument, in this part of the slides, I have it only a bit placeholder, but it's where we will set what are the new data members potentially in our application. In our use case, I will only want to set a method, this onStar method, but yes, that will be specified as a Py dictionary that we will see more in detail in the case of the Qs app. This is only to separate this part of how it's actually a class that it has been written in Python. It's in a .py file, how we can derive from it in C++. So it's we will be creating a new class during runtime that is inheriting from a Python class, and then this class we created in Python 11 because it will be in turn called by the onStar method that we write in C++. It will be called by the Python library code. Yes, so as I was mentioning the links to the documentation, so on top to the Python CAPI documentation for the PyType type. Yes, so a definition for it is like the type objects for type objects. And yes, below the a link also with just mentioning also there in the screenshot the reinterpret borrow. Yes, also here a citation where I got where I just got the code how to do this in a GitHub issue where someone else had initially asked if this was possible to do. And yeah, thanking Wenzel Jacob. I think he is the original author, at least one of the original authors of Python 11, and definitely the author of another more modern library for interoperability between C++ and Python called Nanobine. That can also be used for this kind of application that I'm doing, like using creating bindings for Python for C++ code, or also using Python code from C++. Yes, so that was the part for inheritance. Now let's start by introducing the asynchronous components. So let's see where is the entry point in the app class in the app.py file where asyncio is used. And yes, so I'll be showing that by using some code snippets taken from that file from the app.py and just trying to model it. So just leaving the parts that are important to understand a bit the flow between running code that is written in C++ and code that is in the Python library, and extracting that into a sequence diagram in a couple of slides. But yes, so on top I have a bit of code showing how in the C++ program it will look how we get to that entry point that is in the app class, so this run method. So a bit similarly to before, I think I don't have a line highlight here yet, but yes, I'll run through the snippet on top. So already in main function, so we get the scope interpreter here again. Now I'll be importing the specific app class that is created. So here I'm still naming it generically like an app. So an app that we have derived from the app class in batgrl, and then we will see later how this becomes more specific by having there like a cubes app, for instance, or later an RPS app. For the cubes app, we will see the name with the creation via inheritance for sure. But yes, so once we have the Py object that represents the class in there, so that's imported in lines 5 and 6. In line 7, an instantiation of that object is happening, and I'm showing in there a parameter that is relevant when we are having these apps, which is like the render interval. I think we can think a little bit about it like the frames per second that we want to have. And also just to illustrate here how keyword arguments in Python via Python 11, how they look like when we use them in the C++ code. So there is this underscore A, and this underscore A we make accessible by the using namespace that is on line 1. And yes, so once we have this instance of an app, right? So this would be an instance of a class that we have inherited from app. So we get this run method that we are going to see now in a moment from the app class. So we can just call it. And now, so we see there in the snippet below part of the run method, but so one thing that I want to highlight here is the run method itself is not an asynchronous method, but inside it, asyncio is used in order to run an asynchronous method, which is the run async. And we see a bit more on the next slide. So first, from lines 1 to 3, just a repetition to see the connection before the connection between the main function in C++ and then run. And now here we see run with the run async, which is an async def method. And yes, so if we look into the run async method, so all the way down is where we are having this onStar method that I was mentioning before. So that onStar method is an abstract method in Python. It's not implemented. It's the method that we are going to be implemented in C++ using Python 11 to just to make our animation. So we specify how they look like and also if the logic that they have. And this method is run with asyncio gather, which is running in parallel the asynchronous tasks that we are giving as parameters. The awaitables, I should say, in general, but yeah, synchronous tasks, I think, is also generally understandable. It's also in asyncio task is also a specific type, and the arguments don't need to be specifically type tasks. They need to be awaitable. But yes, so we have this onStart that we are going to be seeing more in detail that is called together with auto render that I'm showing there also a little bit of a model of how it looks like, since I think it illustrates well what is going to be happening after all in the animations app, right? So we have just in auto render is like a infinite loop, and then it's having the render part where it's the library code, batgrl is deciding how it's not pixel because this is like terminal animation, right? But how each position in each line and each column needs to look like at each frame of of the running application, like the character and the color. And yes, just giving a bit more of information of how batgrl works internally. So this is done by having some tree of widgets or gadgets, depending on the version of batgrl that you are using. They were called at the beginning widgets and then gadgets. I'm also mentioning this so when I was doing the cubes application that I will be showing a bit here, so I was using an earlier version of batgrl. So there maybe we will see in the snippets widgets, and then in the RPS app it will be shown as gadgets, but they refer to the same. Okay, so with all that, we can build this kind of a diagram to get a high-level idea of what is happening. So there on the left-hand side, I have like over-specified the part of the user and interaction with the console. And then, so I'm mixing a bit like source time views, so actually source files with the extensions to represent what is on the C++ land and what is on the Python land. And then on the y-axis, we have just the time going on, right? So lower is later in time. So yes, if we run through the diagram from left to right, so we start just at the terminal running an application, so a compiled C++ application that of course has the entry point in main. And then in the main function, we will be calling a run from the app class via a specific app that we have inherited from the abstract base class app. And then at some moment, right, like that will arrive to the asyncio gather that we saw, and we'll call onStart that we are implemented in C++. Okay. So now, in order for that to work well, so onStart needs to, let's say, it needs to conform to a certain interface to be usable with asyncio gather. So in particular, it needs to be like an awaitable. So now we see how I implemented that, which is also based on work of another pull request that I'll be citing on the next slide too. But yeah, so what we need to have is that onStart returns a object of this type. So what is important is that it returns an object that implements the await and next methods. And this is a bit how that can be organized. So the awaitable, it has a data member as a standard feature, and then with void, just so we are not really returning any value from onStart that is used in there from the gather. Yes, then we have there the constructor from the future, and then await method is just returning a pointer to this object. And finally, the more interesting part in this part is the next function. So in the next, first like blocking, waiting until the future is done, and then throwing exception of type stop iteration that in PyBind 11 we have already a binding for it with this Py stop iteration. And that's just essentially how coroutines and also like generators that in Python are used to build coroutines, how they signal that they are finalized by throwing this stop iteration. Yeah, so that was how the awaitable looks on the C++ side, but this code will also be called from Python, so we have to make it explicitly available using bindings. So this part of the interoperability that we are dealing with more, it's actually like making code that we have in C++ available for Python. And yeah, so this how that looks. So I just put it in this, well, this was also suggested like this in this pull request, this enable async function. So it's getting a module that we will see later how this is created. So it's going to be created in a PyBind using a macro called PyBind 11 embedded module. So this is essentially the module that we will also use to put the specific app that we are creating. And we are putting this code in modules. So even if we are writing the code in C++ and this the entry point that we are using is C++, is because this part that we are writing in C++ needs to be called also from the Python side. So it needs to be put in a module in there. Yes. So there is this template class underscore use with the awaitable. So with the type in C++, we give the arguments, the module, and then the name that we want that class to have on the Python side as a string, and then just bindings for each of the for the constructor, and then for each of the two methods in lines 3 to 5. So we see that the await and next are, let's say, bound to or map. Sometimes I think about it also like as map, yes, with to this double underscore method. So these are the special naming that Python uses for some methods. And yes, so this I learned in from this pull request that someone opened, I think, in 2020, but that was never merged eventually into PyBind 11. So it's a pull request that is closed, but it works in there. And one difference with respect to that is in the pull request, there is also yet another method that is written in the awaitable and also bound here is the iter method. But just during my experimentation to get everything eventually to work, I realized that that method was never called. So I mean, I was just like putting some prints when I was trying to get the stuff working with coroutines, putting some prints when the await and next and iter were called, and then I just realized that yes, well, I mean, realized the observation from experimenting was that iter was never called. And yes, so I think this reference that I have there in the last line, so the Python enhancement proposal 492, that is about coroutines and async await. So it talks about how coroutines are built on top of generators and so on. I think it's good to understand also that part. So essentially, it's like a weight is mapped into iter, or the other way around. Iter is put as a weight. So I think the iter part comes more from the generator interface. But for this application, I didn't need to use it. Okay, so now, so we have seen this kind of two ingredients, the inheritance part, and then how to make a method compatible with Python. So a method that I implement in Python 11 compatible with Python's async.io, so that it can be called from the gather. So now let's start putting these two pieces together and also implement a particular on start, which is the part that also I had left like placeholder. And yes, so this we will be doing finally building to this app that I have been mentioning, the Cubes app. So on this slide, not a lot new yet. So it's just still member sign deferring to the next slide. What we see there is the actual type of member. So just a Python dictionary. But yes, so in the PyBind 11 module, so that the code that we put inside here can also be used from Python as we need, right? So the onStart method is called from not from run directly, but from run async. And so we are implementing this in C++, so we have to make it visible to Python. So we put it in this module. But yes, so enable async on top. Place all that the on start that we start seeing more in detail for this cubes application in the next slides. And then the inheritance part once again, right? So in 11, 7 and 8, importing the base class, so the app class. Then we have the part of creating this meta class that allows us to instantiate new classes that we will be able to use from Python at runtime in C++. And yes, so that in lines 11 and 12. So actually using the meta class to create the cubes app. Now, so here let's go to the on start. So just a bit of repetition. So let's say this will be this slideware, right? Like the Pybind 11 module, we will have only one macro, and then the part, so this part that I'm showing here would be like lines 5 to whatever, whichever lines it takes, or we can also just be using functions to organize the code, but all this will be in the same Pybind 11 module macro. Okay, so there we have members, and that's how we are gonna write on start inside the members dictionary. So key on start string, just denoting how the method will be called, and that matches to how it is being called from Python, and also like the abstract method that we find in the app interface and implementation. And yes, so to denote that, that will be a method or a function in general. So we use this Pybind 11 C++ function, and the first argument that we give to this PyC++ function is a lambda expression. So we say that the lambda is going to be returning an awaitable, and now we get into some more details of how the cubes app is gonna look like. So for the cubes app, I am using a cube renderer that is part of another animation that the author of batgrl built for a puzzle from Advent of Code 2 years ago or so. So there is a module that is not directly included in batgrl, at least I believe. But I found it in an example, so already written in Python. And this is just essentially taking care of how cubes need to be graphed on the screen given coordinates. So cubes are going to be defined as a 3D point, so denoting the X, the Y, and the Z coordinate. And then it's also having some logic of, so there is a camera, and then it's like deciding how the cubes look as this camera is moved by just clicking on the screen. That is using a component, so another class that is in the batgrl library called the grabbable behavior. We will see the reference to that also with the GIF to the GIF or GIF to the cubes app in a couple of slides. But yes, so we are importing this renderer module, some Python code. Inside the module, I'm getting the class and then instantiating the class. So here, once again, is I'm using the keyword arguments with this underscore A, and just giving a bit of an idea of how other part of batgrl looks like is how we organize our the visible components that we have in the application, right? Like these widgets or gadgets. So we are kind of making, we can make a tree with them, and then specifying how much space in the screen they occupy with respect to the parent widget or gadget that we have. So that's what is these two numbers, the 1 and 1 denoting is like the proportion that they take on X and Y of the parent. And in this case, the renderer will be added to the app directly. So that's going to mean that the renderer in this application. So yes, I'm trying to show things like are a bit complete, but then they are simple. So then, yes, it's just only this one widget occupying everything. And there are two last parts that I would like to show of the 3D Cubes app. So how the future that is inside the Awaitable that we return from this from on start is created, and then so that would be like general for the batgrl apps that we are doing, or in general to use a method uh, in C, so to use asyncio using Pybind 11, if we need that Python code is Python asyncio code is calling something that we are implementing in C++. So that's the part for the future. And then would like to show how the connection between having the coordinate data in C++, how we pass that into Python. So this part of the coordinates is what happens in these get cubes. So the renderer has a data member, which is just a list of cubes. So it's like a list of 3D points. There is also a color associated with them, but just list of just essentially points in 3D or 4D. We count the color too. And then we will see on the next slide how the data is explicitly specified in C++ and how that is passed into Python data. And then here the future part is on lines 7 to 9. Let me see. Yes, so here adding the renderer in the app, and then the future part. So in this case, we don't have yet any asynchrony in the onStar method. That is, so the onStar method is not being resumed and then, sorry, is not being suspended and then resumed, which is something that will happen later when we have that the onStart is a coroutine. But at this moment, we are just like setting how the application, how we want different widgets of the application to look like, feeding some data from C++ at once and not changing that data. So we have this empty piece of asynchronous work that I'm putting in there in that feature, and that's what is returned. And yes, so finally here the part of specifying the data points in C++. So yes, in there, so there are 4 points for this case, one per line. So X, Y, Z for each of the points. And then inside the cubes, there are NumPy arrays of of size 3. And then so we are mapping the coordinates from C++ into the NumPy array by using this other binding for NumPy arrays that Py11 provides. So we use this PyArray in the first argument, specifying how many elements the array is going to have, and then in the second argument, so memory address to the first element of the array. So a bit of a kind of like C API, or yes, it's to specify. Okay. And essentially, yes, so that's there are several points. So there is a for loop in there going through the size of the array to get in blocks of 3 each of the coordinates. Just to give a bit of an idea of how this simple application looks like, and what I was mentioning before, the grabbable behavior that is in the in batgrl already implemented to have this this kind of feature of a terminal application that you can just click, drag, and it changes like the camera position, right? So for this kind of features is what is interesting to be using a library that has these things. Okay. So now we switch into the next application, so the rock, paper, scissors. So this was a toy program, let's say, to use C++ 20 coroutines together with Python tasks. And with it is how I got, let's say, the challenge of, okay, how can I do a co-await of Python tasks? And then when I am doing C++ applications using batgrl, doing a co-await of tasks is not like the task that happens here with this animation. Is not what I commonly do, but is I need to do co-await of async IO sleeps. So the problem that I solve here is equivalent to that, and then we see also once we get to the co-await of these animation tasks is extended in order to also do co-await of async IO sleeps. So yes, there is this other class in batgrl. Is quite simple, animation class, and it's just a sequence of frames and associated durations. So it would be like it's just doing a bit under the hood, deciding what frame is visible, and then doing a sleep for that duration. on the left-hand side in there we have the code. So there are two functions. One of them is not an async def, so it's not asynchronous, but is returning an async IO task. And then the other one is the async def function. So we will be using this async IO tasks into steps for the same application. So in the first one, it will be with explicit callbacks using API of the async IO task. It's called add-on callback. So we can specify with giving some a callback. So giving some function as parameter what we would like to do or what we would like to happen after the task has finished. And then, yes, so we will improve on that by using C++ and the core routines and just have it how the application look like in there in a GIF. Okay, so we get back into the OnStar. So this part also, this application also needs, of course, the inheritance part and the enable async. So those here I am omitting, and also to get to the application that was to the visualization that was shown in the previous slide. So there is some setup of background color of images, a static image. So apart from the images that the animations are made of, there are also images that are shown in between the animations. So once one animation stops playing and then the next one starts playing, so there can be a transition in there. That one might be omitted just by tuning the durations of the first and last frames in the animations. But more importantly, if we don't want to have it like in an infinite loop, or we want to start the animations after a certain timeout at the beginning, so just to have some static background of an image in there. But yes, so that I also implemented in this kind of C++ code is using Python 11, and I'm not showing it here in the presentation just for the benefit of time and also a little bit of focus on the asynchronous part. But yes, if we compare that to the Cubes app, so this part of the setup would be equivalent to or analogous in a way to the setup of the cube renderer that we saw. Even though in that one, so most of the logic was in Python, so it was just like the imports that were in there. In this case, there is more logic in C++, so I am loading a specific PNGs for the images and also creating animation specifying with a list of floats, which is the duration and so on. But yes, that is omitted here. And we get to the part of just how animations are selected at random, and then how an animation is played using the API from the previous slide, the API of animation, so this play method, and then dealing with the return value that we get, so an animation task. So first there in line 7, so there is this call to next. So next we will see in detail in the next slide, but it's just a very simple function. So just drawing at random one of the animations that it gets from this animations array that gets as an argument. Now, once you have this one of the animations that has been selected, so it's there is this data member is visible that is set to true, and then the animation is called to play. So what is happening in there right away when there is this play, this creation task is like scheduling that job in Python's asyncio event loop to start playing at some moment, and that is relevant to take into account when building this application, because when we are online, let's say hypothetically, obviando here, there is nothing on line 10, the animation has most likely not finished playing yet, right? So if we would like to have this kind of loop of animations, if we will just do an X on line 10 and then change to is visible another animation and play, that wouldn't really look like what we want to have, that there is the animation for rock, for instance, and then that one finishes, the next one goes. So if we start changing the is visible from true to false, and or just leave both of them in true, what we would see is like the animations overlap on top of each other, or that one of the animations is not visible anymore while it has not still played. Yes, so what I mentioned about the next animation, so just doing the random draw, so a couple of objects in there to do the yes, random number generation of an integer in C++. And yes, so then from the animations array, just using that integer that I get from this rand int 0, just a way that I think a bit concise to use. Probably not the best way of doing it, but at least in the application for this, it worked well. And yes, getting the animation as a pi object, and that's the one that is returned. So now let's see how this looks when we use the add-on callback in a very, very explicit way. So we have the three first lines that we saw before. So we get this animation task, and then once we have the animation task, so we use add-on callback to schedule a job that we want to happen once this animation has finished. So then do a bit similar to the three first lines, but also in this lambda expression that we use in a similar way to how the onStart is specified. So the callbacks that are specified with add-on callback, we can do it with a lambda expression that we are giving as an argument to PyCPP function. So I'm capturing also the previous animation so that I can set the is visible to false when it has finished playing. So now if I want next animation, right, to have a 3 or 4 or whatever, so this is how it looks. Probably not the best way of doing this, so there should be like some, there is surely some more concise way of doing this, putting this code in a function and having either by lambda capture or some kind of static integer that just at some moment stops playing. But so with this, what I'm trying to illustrate is that even we would be doing the code like syntactically a bit more, yes, in a different way by reducing this into a function instead of like having new indentation levels every time I want to play a new animation. So it's just a bit the change that one can have by using async await syntax that in C++ we have from C++20 with the co-await. That is, we can think about the code without thinking that there is a new call happening inside a previous one. So it's like this sequential or more code that we are used to from imperative programming, perhaps, or in general, I think. Yeah. So this is what I try to illustrate here, comparing the top with the bottom. So part of how it was looking with add-on callback, but now how it will look in a more sequential way with using co-await. So by using co-await in there, then we will be solving this problem that when we arrive to the next line, then play has finished, right? So with co-await, we will be saying, okay, stop here, so suspend, and don't continue until this task has finished playing. And that was a little bit like the whole goal that I had when I started looking into this interoperability problem. So we can do some terminal visualizations like the cubes app without having this part of C++ routines. But yes, this was a little bit how the project idea originated, right? Like the parts that I saw in Python with await of an animation play. Would it be possible to do that with co-await? And yes, so at least to the best of my knowledge, that's not something that tools like Pybine11 offer under the hood directly. But yes, I think it should be is a future of in the scope within those kind of tools. Yeah, so now when we are doing co-await of the animation.play, so then onStart becomes a coroutine. So there are some parts of the code that we have to change in order for that to work. So that will be there will be a part that we had before, the awaitable. So the awaitable was the return value that we had on start. So we have to modify that so that on start is actually a C++20 coroutine. And then there will be a new part that we need to introduce. So we are doing co-await of the animation.play. So the animation.play, it is returning in Python land an asyncio task, but with PyBine 11, we see that as a Py object. So we have to also write some code in order for a Py object to be compatible with a co-await expression. And that's what we will be seeing through this slide. So yes, first of all, the part of the awaitable. So in the awaitable, we had this future, and then we had also the await and next that I was conforming with asyncio interface to be to be called in the asyncio gather. And now, so that we can have it with co-awaits, we need this promise type, and then in the promise type we need to implement some function. So at least in the solution that I have arrived at, this is how I have managed to do it. So initial suspend and final suspend, quite simple. I'm not doing anything special there, just suspend never. I still don't want that the coroutine returns anything, so return void is the one chosen, and then not just also like an empty method, a bit of error handling in unhandled exception, and then just making a connection with putting a promise, a stud promise inside the promise type, and then the future that the awaitable was created, I get it from this promise. So that's on line 7. So getting the promise, get future, and that's how the future that we see in line 2 is created. Then await stays the same, so it's just a return of this as we had before, but next needs update, and this is what I was mentioning at the beginning, that I don't think I have tried to do it in a better way with a stud condition variable, didn't manage to succeed, but I'm pretty sure that there should be a better way of solving this by having a explicit timeout, which is what I'm going to show you next. But first, motivating it. So before in the cubes app, so there was no like asynchronous state in the onStar method. OnStar would be called once from Python. It does the job and it returns, and that's it. There is no, it's not suspended and resume. But now with using co-await, this is different. So if I would if I would leave it with future await, that would block the application. Let's say it wouldn't work, or perhaps not all the part of the application, because we have this auto render and so on that is running parallel in the event loop. But the animations that we are writing in the in OnStar, they wouldn't continue. So now in next, what I have is this wait for of the future. So I'm just checking every 3 milliseconds. So that's a parameter probably a bit. So I found that good to work for my application. So in the pull request that I mentioned before, initially this was not with future await. That was something that I refactor for cubes for applications like the cubes app, that they don't suspend and resume, but there was a wait for 0 milliseconds, and that so just by using it in the computer, like the applications work and it's good, but I mean I hear the fan of the computer starting to work, and if I monitor the application with htop, so it was spiking, right? Like it was using 100% of a CPU. We'll wait for of 3 milliseconds, so I don't hear the fan of my computer at least. And I also see that the load is not going. It's just as if I was not, as if it was like in the cubes app, not really a difference. And also importantly, at least for the animation that I have been doing so far, the awaits that I am normally doing for the visuals itself, they are longer than this. So this is what worked for me. But yes, even if I, from a use case point of view, at least I haven't done an animation yet where this has been the bottleneck. I think it would be more elegant and also more suitable to be using coroutines to have this without that explicit wait. But for the moment, I haven't managed to do it. When I stopped experimenting with this back in August, I tried something with a condition variable, but I think I had some misunderstanding in there how the threading works under the hood for here. So because that was leading to deadlock when I tried to have a condition variable around here. And yes, so the part of the for that we can so that it's possible to co-await of a Pi object. So that's a bit how it looks like. So I'm creating a new class, Pi awaiter. And yes, so I am putting inside the Pi awaiter a Pi object that is a task. So this is how the constructor looks like. This part of the solution, let's say, a bit more proud of it, or I think it looks more elegant in the await suspend, because I think it fits nicely the add-on callback interface of the async.io task with the resumption of using a C++ coroutine with the coroutine handle. So there in the add-on callback, and just essentially saying yes. So when this task finishes, just call the handle.resume. With the highlight here. And yeah, so and other two functions, but yes, like the logic here is a bit more, let's say, trivial in a way compared to the await suspend that we just saw. So await ready is just checking if data member that is already available in the tasks API. So if it's done, we see other, I don't have highlight here, but yes, on line 6, we see another detail of Python 11 interface. So we get the objects, and then if we want to have them in a particular type, so we can just use this cast method. So in this case, it's a cast tool. And then the await resume, so just returning a task result in case we would like to use it, and then just doing some error handling in there. And final code that I have here. So this Pi awaiter that we saw so far, it would work if we are getting a Pi object that is an async.io task, like the one that the play method return. But in the animations in general, and also like if you put grep for await in batgrl library, what you are going to see is await of async.io sleep, what is used in most cases. So this Pi awaiter is not compatible yet with async.io sleep, and this is a way of doing it. Probably also not the most elegant solution to have the if here, but this could be probably just a bit more easily refactor, having a couple maybe of subclasses of Pi awaiter or so. But yes, so it's just checking inside the Pi object of what specific type it is using these strings. And yeah, so if I get a type that is a coroutine, so sorry that I was checking if it has line highlights or not, but yeah, in line 8, so if it's a coroutine, so then I'm assuming that it just comes from the sleep, because it's what I am, the two cases that I am having. But yeah, in general, if it's a coroutine, so then it just schedules it in the event loop by using the create task. And otherwise, it just assumes that it's a task directly. And that's what the Pi awaiter that is also possible to do async.io, a co-await of async.io sleep, co-await of async.io ATTR sleep, more precisely. And yes, so that was all the code and all, let's say, the solution to use C++, to use Python async.io from C++ via Python 11. And yes, so some summary of it and conclusions. So this has been about leveraging Python from C++ in contrast to the other typical direction of using C++ from Python because of its efficiency benefit. Yes, just I think one perhaps strong point, right, or advantage that the C++ coroutines, C++ coroutines are a bit lower level is that yes, so with I don't think a lot of code, right? Like after all, I have this in a header and it's probably around 50 lines, surely under 100 lines. So you can make it work with other asynchronous controllers, even if they are in other programming languages. So I think this is attractive because there is quite a bit of code already written in Python. In Python Asyncio, that can be nice to use directly from C++. And yes, so this was also something that I didn't expect, but something that I learned while doing the project. So I think the motivation of the async, of the await part, it clicked much better, at least for the use case of callbacks with this RPS application. And yes, so yes, I think this is just kind of actually like kind of fun to do this like programming puzzles with terminal graphics and also learning a bit on the way the modern C++ future. So it was have been enjoyable. So yes, thank you very much for the attention, and sorry that it perhaps took a bit too long eventually. Thank you.
Thank you much. Thank you very much. That was a great talk about interplay of Python and modern C++.
Thank you.
And yeah, we're a bit over time, so